Hi there, stargazers. Welcome to the first episode of Fansci.
We are your hosts, Fadi and Nandi.
Hold on to your screens as we orbit through cosmic history.
Today's cosmic quest: centrism. What is really at the center of it all?
Spoiler alert, it's not Earth.
Give me a word. Any word, and I show you how the root of that word is Greek.
Heliocentrism, from the Greek words helios meaning sun and kentrikos meaning center, is the idea that the sun sits at the heart of our solar system.
Sounds obvious now, right? But for centuries, people believed in geocentrism, that Earth was the immovable center of the universe, that she was that girl.
It wasn't until the Renaissance period that heliocentrism finally took the spotlight. So how did we get from an Earth-centered to a sun-centered system? Let's rewind.
Around 340 BC, Eudoxus of Cnidus imagined the heavens as a set of 27 concentric spheres. One sphere for the fixed stars, 3 each for the sun and moon, and 4 per planet. These spheres explained rising, setting, and orbital motion, but not retrograde motion.
That's when a planet seems to moonwalk in the sky. It's just an illusion, caused when a faster moving planet passes a slower one in orbit. All planets orbit the sun in the same direction but at different speeds. Eudoxus didn't have the tools to explain that yet.
Aristotle entered the chat and boosted the sphere count to 56 and claimed they were real crystalline shells made of ether, a fifth element.
He believed in a perfect, unchanging universe, but even with all those spheres, he still couldn't explain retrograde motion.
Meanwhile, Heraclides of Pontus had a radical idea. Maybe the Earth is spinning. And maybe Mercury and Venus orbit the Sun. I think he's onto something.
Fast forward to 150 AD, Claudius Ptolemy arrives with a more complicated, more confusing, more accurate vibe. A supercharged geocentric model with epicycles, small circles along orbital paths, and eccentrics or off-center orbits. Think cosmic doodles.
He even used an equant point to keep planetary speeds consistent. This made his model the most accurate of the time, even if it was still Earth-centered. Ptolemy dropped the spheres, but kept the celestial one holding the stars. Talk about attachment issues. In other places, scholars were developing their own models. Some showcased similar ideas to Ptolemy, while others took a different route. Arab astronomer Al-Khwarizmi preserved and expanded it through his work Siege al-Sindent, while Ibn Yunus of Egypt in the 1st century said, some of this doesn't check out. He developed the Hakimeter tables, which had many detailed observations of planetary positions, which led him to questioning parts of Ptolemy's model. His work subtly paved the way for future critiques on geocentrism. By the 16th century, the Ptolemaic model wasn't quite cutting it. Planetary positions were off, and orbital times just didn't line up logically.
Enter Nicholas Copernicus, who proposed a bold new idea, the sun being at the center. Earth spins on its axis and orbits the sun like the other planets.
His model explained retrograde motion naturally, no epicycles needed. But he insisted on using circular orbits and complex mechanics, and people weren't fully convinced.
What's wild? Ibn al-Shatir, a 14th century Syrian astronomer, had created a geocentric model very similar to his heliocentric one.
Tycho Brahe, a Danish astronomer in the late 1500s, didn't buy heliocentrism. Why? No observable stellar parallax, the apparent shift in position of stars due to Earth's movement around the Sun. It's a key piece of evidence for the heliocentric model, but he could not observe stellar parallax.
So, he proposed a compromise. Planets orbit the Sun, and the Sun orbits Earth. A solar sandwich. He also made observations of a supernova in 1572 and comets in 1577, which challenged the Aristotelian belief in a perfect, unchanging heaven and the existence of celestial spheres.
Brahe's super-accurate data helped his assistant Johannes Kepler prove heliocentrism. Kepler used Brahe's Mars goldmine of data to develop 3 laws of planetary motion.
1. Planets orbit the Sun in ellipses, not circles. 2. They move faster when closer to the Sun, sweeping out equal areas in equal times. 3. A planet's orbital period squared is proportional to its distance cubed.
Kepler's work confirmed heliocentrism with the physics it desperately needed, fundamentally reshaping astronomy. But there's more.
In 1608, the telescope was invented in the Netherlands. A year later, Galileo Galilei built one and pointed it to the skies.
He saw craters on the moon, sunspots, and Jupiter's moons orbiting, wait for it, not Earth. Everything didn't revolve around Earth.
One of his biggest flexes, he saw Venus go through phases just like the moon. That only made sense if it orbited the sun. Galileo was all in on heliocentrism. He also discovered new stars, which dissolved the celestial sphere.
He supported the Copernican model through his observations and threw shade at the geocentrism one. Then came Sir Isaac Newton in the late 1600s, using his law of universal gravitation, which simply states that gravity pulls more strongly between heavier objects and gets weaker with distance.
Using this in his 3 laws of motion, Newton showed how gravity could explain Kepler's laws of planetary motion. He showed that a planet's changing speed in its orbit is due to the gravitational pull from the sun, which becomes weaker as the distance increases. Basically, mass attracts mass, and the sun being big, hot, and spicy, it kept all the planets in orbit.
This solidified heliocentrism and its ability to explain how and why the planets move as they do.
Funny enough, way back in 300 BC, Aristarchus of Samos had already suggested Earth orbits the sun. He didn't have the math or the tools to prove it.
It took 1,800 years and a scientific revolution just to catch up.
The journey from geocentrism to heliocentrism was long, winding, and full of cosmic curiosity. It reshaped not only how we see our solar system, but how we study the cosmos at large.
Thanks to ancient philosophers, Renaissance astronomers, and modern physicists, we now know planets orbit the sun and not us.
But the universe still holds mysteries, and we're still finding ways to explain them.
Whether it's through Newtonian mechanics, general relativity, or yet to be discovered theories, the cosmos continues to challenge us. We're still searching for answers, and when those breakthroughs come,
Fansai will be here to break them down for you.
Until next time, keep your minds open,
and keep your eyes on the stars.
and if it's the sun, use SPF. Hi there.